Okay, so I just want to go into sort of the basics of sequences, sequences in general, not specifically arithmetic or geometric sequences, but just like what a sequence is, how we write them, sort of the terminology and like the vocabulary and understanding what that means, and then what you do with them, basically, just so you have some basics. So first off, when we say we have a sequence, what does that mean? Well, a sequence is just an ordered list of numbers, and there's a pattern. That's what makes it a sequence, is that there's a pattern to how those numbers are created. So the Fibonacci sequence is a very famous sequence, and there's a specific pattern that you use so that you can get to the next term. So each number in that list is called a term, and we use a sub I, where I is just like an index. But that's how we call each term, that's the notation. So that subscript I is the index. It basically tells you what position in the sequence you are, whether you're the first term, the second term, the third term. So we usually start counting at 1, so that you have A1, A2, A3, but you can start counting at 0. It's not as, in math, with sequences, we generally don't, but you can. You just have to make sure that everything is adjusted in terms of that, because all the formulas that we have with sequences assume you're starting at 1. So if you're not starting at 1, if you see something that's like an n-1, you now have to adjust it. So now it's just n instead of n-1. So you have to make sure that you make the right adjustments so everything works out. So I would just always start by 1, so you don't have to do anything like that. Otherwise, you get what is frequently an off by 1 error, which people in programming are very familiar with. It's very easy to be off by 1 in programming. And then these subscripts, because we're counting what position they're always whole numbers. They're not negatives, because we don't really have negative positions, though depending on where you start, you can rename them so that you have negatives, but it doesn't really make sense. So that's what a sequence is. An infinite sequence just means it goes on forever. So we use 3 little dots or ellipses to just indicate that it keeps continuing. And so we usually write it where you write the first few terms so you can kind of see the pattern. And then you write AN, you basically write what the formula is to get the pattern. And then you have dots just to show that it keeps going. And then a finite sequence means that there's a specific number of terms and it ends, and so then you just don't have those 3 dots after you give the formula. So AN is basically the formula, the pattern you use to come up with your sequence. So you give the first few terms so you can kind of see it in action, and then you give the formula. So you always, if you're giving a sequence, generally we always want to make sure we write down what that formula is, what that nth term is, because otherwise it's not really useful. I mean, you'd have to then go back and try to figure out what the sequence is and what that pattern is. It's a lot easier if we just give it to you flat out. Like the Fibonacci sequence, we don't generally give that pattern, but people are familiar enough with that sequence that you know what it means. So basically, you're adding your previous 2 terms together, and that gets your next term. So, and that's actually sort of a recursive sequence because you're adding the previous terms, and so you need those information in to get to the next one. But in general, if it's not a famous sequence, you want to make sure you give the formula so that you know how to create the sequence. So the book describes sequences as being like a function, and they are like functions because they're like equations basically, and you can graph equations. But the difference is that when you're graphing a sequence, because we're only plugging in whole numbers, because for our terms, we don't have, it's not continuous. You're graphing ordered pairs. So your graph is not connected. It's just a series of ordered pairs when you're graphing a sequence. So I have a link here that demonstrates sort of how you can see these. It's helpful just to visualize what sequences are. I'm going to pull this over. You don't have to graph sequences, but here's just an example. of how you would graph a sequence, because you have to do it just by ordered pairs, so you're not actually like connecting the dots. So in Desmos, it gets kind of complicated because you have to write in your formula, then you have to basically create a list so that you can do dots instead of just connecting it. Because if you didn't have any of this, it would try to connect this and allow values for n that are like decimals, and we don't do that when we have sequences. So this is actually, if you click this menu button, there's a whole bunch of examples, and some of these will be helpful later, but I think this is actually where I found, oh, maybe not, maybe it's not on this. It's similar to lists right here, where you're plotting a list of points. So because that's essentially what we're doing. So it's very similar. And if I open that one up, you'll see it's kind of done it the same way. But I've created this Desmos graph that you can use if you just want to visualize what you're going on, what you're looking at. But you don't have to use it. It just kind of helps if you're a visual kind of person. So when you go on to calculus, you often talk about things that converge, and a converge means that they are approaching a single number. And so if you have a sequence that converges, that means like your pattern is getting close to one single number and like repeating at that number. And so the graphs can kind of help you see that. It's very similar to an asymptote, where as your graph like zooms out, it gets closer and closer to a certain point, like with a horizontal asymptote. So sequence convergence is very similar. So looking at graphs can be very helpful for that, but it's not necessary. You don't need to graph a sequence. It's just if you like to have a visual. So I just wanted to include that. So we're just going to go through different types of sequences, how you write your terms, how you use the formulas, and then do some with the recursive stuff, because the recursive stuff is actually really helpful for those in programming, because a lot of programming, we choose to write things recursively because then you can just keep calling the function, and it's, especially if you're doing the same thing over and over again, it saves you space and memory, at least as far as the code goes, because your code is usually shorter if you can do it recursively. It may not necessarily save space in a number of evaluations, because if you're doing a recursive and there's a lot of steps, it has to save all those previous steps. But as far as coding goes, it usually makes your coding simpler. And if you have, like, if you can parallel your coding so that you can shoot off different parts of the code to different places, making it recursive actually is a really great way to do that. Actually, my master's thesis was about a particular type of algorithm that we specifically wrote. It was originally not recursive. We made it recursive with the goal of being able to run it in parallel to speed it up. So intersection of my math degree, it was, you know, we basically took a math formula and we wrote an algorithm and then implemented it in code. So math and computer science are very, very related in those kind of things. But anyway, the recursive stuff is a few slides away. So here, we're going to write the first 5 terms of the sequence. So remember, we start with n equals 1. So what I find helpful is just to kind of write my n and then write them so I remember what number I'm plugging in. So if we want the first 5 terms, we're plugging in a number for n, and you're just plugging in the numbers 1 through 5. So we're given a sub n. This is our formula. This is how you create the sequences. This is the pattern that we use. So you just literally have to plug in your value for n, evaluate your equation, and then that gives you the sequence part. So if you're just plugging in numbers, it's just like using a function. So if we have 2n plus 8, then for n equals 1, I'm just literally plugging in 1 for n. So that would be a -2 plus 8. So we have 6. So our first term in the sequence is 6. Then term 2, you plug 2 in for n. And that gives us -4 plus 8, which is 4. And you can see that our pattern is a linear equation. So if you connect it back to what we know about functions, it's linear. This would have a slope of -2. So we're basically subtracting 2 each time. So even understanding what the formula means in the pattern, you can then say, okay, so the next one's going to be 2, and then it's going to be 0, and then we're going to get -2. And you can plug in your values to verify that. But that is basically, we see pattern, we're subtracting 2 each time, and then this particular formula is written such that your first term comes out to be 6. So you want to note that it's not exactly the same as a linear function, because we have a linear function where the y-intercept would be 8. You'd think you'd start at 8, but we don't, because we don't start at 0. We're starting at 1. So you can't just say, oh, okay, my starting point is 8, subtract 2 each time, because we're actually starting at 1, not 0 when you plug in the numbers. So you got to be very careful about our starting point, because that's the sequence is not exactly starting at the same point that maybe an equation would. So when you write this sequence, if you were to kind of write it out, we would just put our numbers in order, and then you put 3 dots just to indicate that the pattern continues. So I've got 5 terms written down there, and then I have my 3 dots just to say, okay, yeah, that pattern is going to be continuing. So second example here, again, we want the first 5 terms, so I just find it so much easier to create a table. And here it's a little more complicated because we have an exponent going on, we have an n+1. So first term, I plug in, I've got 6, then I've got -1 to the 1 plus 1. So that's going to be -1 squared, which gives me a +1, and then times 6, so we get 6. And then for our second term, we have 2 plus 1. You want to make sure, oops, and I plugged in 2 in the wrong place. This is the hardest thing with sequences, is you need to make sure you're changing the correct number, and I almost changed the wrong number there, so you want to be very careful. So we've got 2 plus 1, which is 3. -1 to the 3rd power is -1 times 6, so now we get a -6. So then we continue. Now it's going to be the 3 plus 1, so that's going to be an exponent 4. -1 to the 4th power is 1, times 6 is 6. And you get enough that you basically see the pattern, so then we're going to have -6, so then we're going to have 6. And this is what's called an alternating sequence, because it's basically alternating in signs. And this would be something that we wouldn't necessarily have as like a function or anything, where you just kind of flip back and forth, but it is more indicative of a sequence where you may have patterns where you're just flip-flopping in sign. Any questions? Okay. So here now we're going to find the missing term of the sequence. And so these are much more complicated sequences. And we're given the formula, and then we're looking for a specific term. So like the first one, it says a sub 16 equals question mark. So you're basically looking for the 16th term. So we're being told n is equal to 16. What is the value when you plug that in? So a sub 16 is going to be -1 to the 16 minus 1 bracket. Let's see, 16, then 16 minus 1. And it looks all very complicated. Sequences do kind of have more complicated formulas than maybe a regular equation would be. I am not sure why this is. It's just in my experience, they tend to be much more complicated than regular equations. But we're just basically following the order of operations here in order to determine what this missing term is. So 16 minus 1, that's going to be 15 in my exponent. Inside my brackets, I'm going to have 16 times 15. So I'm going to just do that on my calculator. That's 240. Now, -1 to an odd power is always going to be negative. So this is going to give us negative 240. So our missing term, the 16th term, is negative 240. Now, on the right, we're looking for A13, the 13th term. So n is equal to 13. So I'm looking for A of 13. So I'm plugging in 13 for n. I need to make sure I plug it in all of the right places here. And then we evaluate. So on the numerator, I need to do 13 squared, which is 169. And then I'm going to multiply that by 4. I'm going to just do that all in the same step. So that gives me 676. Then I have minus 13 plus 3. Then I've got 13 times 12 times 15 in my denominator. So I'm going to simplify the numerator. Subtract 13 plus 3, 666. And then the denominator, 13 times 12 times 15, 2,340. Now, when we have sequences, you don't want to write them in their decimal form. You want to leave it as a fraction, and you do want to try to reduce. I prefer using my calculator to do the reducing for me, because my calculator has the ability to do fractions and it will reduce it, and it just makes life easier, because I want you guys focusing on the math and less on the things like arithmetic and reducing. Let your calculator do that. So when I put 666 over 2,340 in my calculator, I get for the 13th term 37 over 130. So that's how it reduces. So when you have a pattern, it's pretty simple. All you have to do is plug in your values. It's not too complicated. The hardest part is if you're given a sequence and you're trying to find the pattern from the sequence. But most sequences are either arithmetic, where you're adding or subtracting the same thing each time, and we have actual formula for that. Or they're geometric, which means you're multiplying or dividing by the same thing every time, and we have a formula for that as well. So those are the most common types of sequences that you see and that you use. So, you know, if it's not one of those, it's a trial and error. It's kind of like those puzzles, number puzzles or brain teasers. You know, you'll see on the internet where somebody gives you a series of numbers and you're trying to find the next number, and they're like, find the pattern. That's basically what a sequence is. If you have a sequence of numbers and it's not arithmetic or geometric, it's just trying to figure out what the pattern is. And sometimes it's a combination of both, adding and subtracting. Sometimes you've got exponents involved. There's no shortcut or tip on how to figure it out, other than you're just trying to find a pattern and you're trying different things. And maybe you found a pattern for the first two, and then you see, does it work for the third? If it doesn't work for the third, try to fix it. And you just keep modifying it until you get to something that works for every number in your sequence. But it's a trial and error. There's no other way to kind of figure out the pattern other than that. Are there any questions on these missing term ones? Okay. So now the rest of these are the recursive ones that I wanted to focus on, because this is the kind of stuff that you see a lot in programming is just trying to use recursion as a way to simplify your code, and especially that way you can just reuse stuff a lot. So we're going to write the first 5 terms of the sequence defined recursively. So in order for a recursive sequence, in order for you to write the terms, you need to know what the pattern is, and then you need to at least have a starting point. And then from that starting point, you can find the next ones, or if you have to work backwards, you can. So we know that the first term starts at 14. And then we have this pattern, a sub k plus 1, which is telling us the next term equals -2 times a sub k. So recursive sequences, instead of using n, they'll usually use k, just to indicate that there's some recursion going on. So just like I did with the first 5 terms, the first ones we did where I like write down n and then I go 1, 2, 3, 4, 5, I'll do the same thing here. So we have k, 1, 2, 3, 4, 5, and then sometimes it's helpful to also write like k plus 1 or what other things you have in there so that you know what term you're actually finding. So these would all be 1 extra. So notice that k plus 1, that is the next term. So I don't even need to go that far. I already know that the first one is 14. And then I just need to find terms 2, 3, 4, and 5, which are going to be the k plus 1. So I find it helpful to actually plug in those numbers. So we have a sub k plus 1, so that's going to be a sub 2 equals -2 times a sub 1. So I like to plug in my numbers for k and see the formula before I start to try to plug in what my values are, because it just makes it a lot easier to see what's going on. So you can see that the pattern is you're taking the previous term and then you're multiplying it by -2. So we know that a1 is 14. So I'm just multiplying 14 by -2, which gives me -28, and then that's a2. So next step, we're finding the third term, a3, and that's going to be -2 times the previous term, a2. So we have to use that previous information, -2 times -28. And so multiply those. This gives us a positive 56. The advantage to writing things recursively is that it makes the pattern really clear, because you can see that all we're doing is multiplying each term by -2, because that's what that pattern says. The disadvantage to recursive formulas is if I told you to find the 16th term, in order to find the 16th term, you have to find the first 15, because you need to have the previous step in order to get that. We didn't need to do that when it's not written recursively, because we have the full formula, so you don't need to know all the previous terms in order to figure these out. But with recursive formulas, you do. So recursive is nice because you can see the formula, and it usually makes the formula simpler, but the downside is that you can't skip ahead for certain terms. You have to calculate all the prior terms in order to find the term you're interested in. So if you're doing anything with sequences, especially with programming, this is where you have to consider the give and take. Do I want to write something recursively or not recursively? It depends on, do I need those prior steps? If not, you may not want to do it recursively, but if you use those prior steps, recursive might be the way to go because you have to calculate them anyway. So just something to think about when you're doing this. But to continue, so a4 is going to be -2 times a3. So I'm going to multiply 56 by -2. So -112. And it's really easy to get the pattern. I just know that I'm going to multiply by -2 again. And that gives me 224. So our sequence is 14, negative 28, 56, negative 112, 224, and then we'll keep going. Are there any questions?
Yes, I have a question.
Mm-hmm.
On the first one, it's like I got a little behind, so I was like writing the problem when you were talking. So like A2 equals, okay, so what I do, I usually write A1 equals 14, and then I write A2, A3, A4, A5. Okay?
That works. Yep, so I can do that right here.
Yes, like that. So when you started with the -2, that's where I got lost. Because I try to rewrite the AK plus 1, and then to me it says A2 plus 1, which is A3, equals -2 times A2. So
I see. So that's what I did in blue here is I said, okay, I'm actually going to start with K equals 1. So that's what I did on my K first, 1, 2, 3, 4, 5. And then I did K plus 1, which gives me 2, 3, 4, 5. And so that's how I knew that I start with A2 versus K equals 2. I'm really using K equals 1. So I'm still starting with that 1 for K. But when you plug it in and you've got K plus 1, 1 plus 1 gives you 2. So that's how I made sure that I had A2 versus starting with A3. So if it helps you to do A1 equals 14 and write that first and then do A2, A3, A4, A5, that's fine. The thing with the recursive though is that if I wrote A1, A2, A3, A4, A5, it's prone to think that, okay, A2 means K equals 2. But K actually means 1 in a recursive. So that's why I didn't do it that way. And instead, I wrote my K's first and then do the sequence.
All right.
So, yeah. For things that are not recursive, doing A1, A2, A3, that is perfectly fine, and that works. But it's the recursive stuff you end up with an off by 1 error. So that's why I focus on the K's instead. And this is actually, I think you came in maybe after my first one. But I sort of did the same thing here, where I wrote down what numbers am I plugging in. I started 1, 2, 3, 4, 5, and then went from there.
Oh, I see. So I was on then.
Okay, so you did come in for that, yeah. So it's the same sort of thing. I'm writing those down first so I know what I'm plugging in, and then I go and plug it in.
Okay.
Yeah, because with those recursive, you get it off by 1 error, and then you're all going to be messed up. So. So here's another recursive, and this is one where it's a little more complicated because you have to use the prior 2 terms in order to get the pattern. So this is sort of like the Fibonacci sequence. You have to use the prior 2 numbers to get to the next number. So, and this one's also different because it starts with A0 and A1. So this is one where we're actually counting from 0 versus counting at 1. So you do have to kind of pay attention to your subscripts to know where you're counting. So because my first one here is A0, that's going to be my K. So I'm going to just do 0, 1, and then just to make sure that I have enough sequences, I need to have, let's see, I need the first 5 terms. So I've already got 2 terms. So then it'll be 2, 3, 4, and that will give me 5 terms. So I'm only going to pick values for K that are 0 through 4 in order to have 5 numbers written down. Now our formula, we got to make sure that this works because if it doesn't, you need to kind of keep going. So notice our formula has a K minus 2 and a K minus 1. So just to make sure that I have my right numbers then plugging in, I'm going to just also make those kind of columns here. And then I know that my k is 0, so k minus 1 would be 0 minus 1 or negative 1. And then k minus 2 would be 0 minus 2 or negative 2. And then I'm going to do this again. I'm just going to kind of fill in my chart. 1. So if k is 1, 1 minus 1 is 0. And then 1 minus 2, that is negative 1. Then when k is 2, 2 minus 1 is 1. 2 minus 2 is 0. K is 3. 3 minus 1 is 2. 3 minus 2 is 1. And so this helps me determine where I'm kind of starting with my k values. So we know A0 and A1. So I can't actually start with k equals 0 because I don't have a minus 1 and a minus 2 in my term. And I can't use this one because I don't know what a negative 1 is, because I don't have that. I only have 0 and 1. So we have to actually start with k equals 2 here in order to make sure that we have enough patterns. So I don't need to calculate those first two because I don't actually have those values. I don't have a sub negative 2 or a negative 1. I have a 0, but I don't have an a negative 1 to work with. So we're going to be starting with the value 2 for k. So now I'm going to plug that into my formula. So I have AK, so it's going to be A2 because I've labeled my k's over here in that first column. And then that's A of k minus 2. So I have that as in my columns, so that's A0. And then plus AK minus 1, which in my column is going to be A1. And I have both of those values. A0 is negative 1, A1 is 1, so negative 1 plus 1 is 0. So I got A sub 2 is equal to 0. So now k is going to be 3. So for A sub k minus 2, 3 minus 2 is 1, that's going to be A1 plus A2. So A1 is 1, A2, we just solved is 0, so we get 1. A4. So that's going to be A2 plus A3. So A2 is 0, A3 is 1, and we get 1. So now we have 5 terms, because they told us the first two, which are negative 1 and 1, and then we just got 0, 1, and 1. And then we would have some pattern going on. So when I set this up, I always start counting with my k being 0, and then I figure out, well, what information do I have? If I don't have the terms to figure that one out, then I keep skipping until the first one that I can figure out, and that would be A2, because we already have 0 and 1, so the next one we'd be finding would be A2. Some of my math classes that I took where we had to do a lot of programming of different algorithms, and there's some sort of calculus that you can do with approximations, and you actually, there are things called differential equations that you solve by using sequences and plugging in your previous numbers. And I actually had to basically make a table to make sure that I was plugging in all the right values and coding it. And I had to basically do something like this and be like, oh, I don't have that information. I can't start my counter there. You know, like when you're writing programs, you always want to start at 0, but we have to start at 2 here based off of what we're given in order for this formula to work. So you have to it helps to walk these things out on paper and see what you're actually going through and adding together, so that when you're programming, you know where to start your counter. Like if you were programming this sequence, you would have to start at 2 you wouldn't be able to start at 0 because you don't have that right information, and you would get an error trying to code it. So there are questions on this example. Okay, so I've got one more, which is recursive. So we've got also here, this is a factorial. The exclamation point is a factorial. So that is, most calculators do have that. There's a button, or there will be like a keyboard shortcut in order to do the factorial. On my simple scientific calculator, I have to hit the probability button to get the factorial. On my graphing calculator, I think it was like the diamond button, and then I think it was like the division button or something like that in order to get to that. But that exclamation point means factorial, which just means that like 5 factorial is 5 times 4 times 3 times 2 times 1. You're multiplying all of the numbers together, but you subtract 1 each time. So that's what a factorial means. So we're going to write the first 5 terms of this sequence, and we are given, and this one is not necessarily recursive because we're back to the end, but it's just more complicated because we have this factorial thing. So back to n, so I'm going to label my n's, and our first term starts at 0. So we're going to be counting from 0 instead of 1 here when we're doing the first 5 terms. So 2, 3. So that means in order to have 5 terms, I'm going from 0 to 4. And so now to figure out each term, so I know that A0 is -1, so I can just kind of put that in there. So A1 is equal to, now we've got this complicated formula. You've got -1 to the 2 times 1 plus 1 over 2n plus 1 factorial. So 2 times 1 is 2 plus 1, so that's going to be -1 to the 3rd. Oops, and I forgot to plug in for my n here. And then that is going to be 3 factorial. So -1 to the 3rd power, that's -1. 3 factorial is 3 times 2 times 1, and we're going to get 6. So we get -1/6 there for A1. A2, I'm actually going to have to move these down. I'm still running out of room here. So again, you plug it into the formula, make sure that you're plugging in the numbers in the right spot. So that would be -1, 4 plus 1 is 5. And then that's going to be 4 plus 1, so that's 5 factorial. So any negative to an odd is going to be negative, and I'm going to use my calculator to do 5 factorial. And that comes out to 120. So that would be 5 times 4 times 3 times 2 times 1. And you're not going to want to have to type all that out on your calculator. The factorial button is really nice. It makes that much quicker. So we've got 3 terms so far. So now we want to find a 3, which is actually our 4th term because we started at 0. So that's going to be 2 times 3 plus 1 over 2 times 3 plus 1 factorial. 2 times 3 is 6 plus 1. So you can see that there's like a pattern here. And once you've done enough and you can see the pattern, it makes it a lot easier when you're plugging in the numbers because you're like, oh, okay, I see what changes every time. So this is going to be -1 over whatever 7 factorial is. is 5,040. And then N4, kind of running out of room here. But I can see the pattern. I know that I'm going to end up with a -1 over, and then because it's 3, 5, 7, so this will be 9 factorial. So once you get the handle of the pattern, you don't even really need to plug it in anymore. And 9 factorial, 9 factorial is giant. 3, 6, 2, 8, 8, 0. So our first 5 terms of the sequence are going to be -1, -1/6, -1 over 1/20th, -1 over 5,040, and then -1 over this big number. And those are the first 5 terms of the sequence. Are there any questions?